Okay, good morning, good afternoon to everyone. Welcome to the new session of the online meetings of the Worldwide Energy Network, WENER. Today, we will have the presentation of Professor Dr. Venkata Yaramasu from Northern Arizona University in the US, with the title Permanent Magnet Synchronous Generator-Based Wind Energy Systems. Professor Yaramasu received his PhD degree in electrical engineering from Ryerson University in Toronto, Canada in 2014. He is currently working as an assistant professor at the Northern Arizona University in the US. His research interests include renewable energy, high power converters, variable speed drives, electric vehicles, energy storage, smart grids, and modulated control. With him, today we will have as a panelist also Dr. José Luis Elizondo from Instituto Tecnológico de Monterrey in Mexico, en Pemex Mexicanos, Professor Rubén Peña from the University of Concepción in Chile, and Professor Frede Blabjer from Aalborg University in Denmark. Venkata, welcome. Thank you for being here. And one more thing for the audience, if you have any question you want to ask to the panelists or the speaker, you can write them in the chat in our YouTube live or Zoom, and later we will proceed to ask to the panelists. Venkata, thank you very much and welcome.
Thank you very much, Marcus, for the introduction. I will jump to the next slide. In this presentation, I'm going to talk about permanent magnet synchronous generator-based wind energy systems, a brief overview, and then I will talk about power converters in two categories, low voltage and medium voltage, and then I will talk about control schemes for PMSGVX. I will talk about classical controls that are currently used in the market, and predictive control and modulated predictive control, which are very promising for future deployment. Lastly, I will talk about future trends. Most of the information in these slides is taken from two books. So the first one is my book, and the second one is from Bingu. So for those new to wind energy, so the wind turbines, they convert wind into kinetic energy through aerodynamic process. So here the kinetic energy in the wind is converted to the mechanical energy. The speed of the wind turbine blades is very low, usually 15 to 20 RPM. In order to increase the speed, we use gearbox. The output of gearbox is connected to a generator. The generator output voltage and frequency are varying with respect to the wind speed, but on the grid side, we need constant voltage and constant frequency. For this purpose, and also to extract maximum possible energy from wind and to comply with grid codes, we use a power converter. And the output of the power converter is usually less than 4,000 volts. But in order to connect to the grid and transfer the power at maximum efficiency and lower losses, we need to step up the voltage. So we use a transformer to step up the voltage, usually from 690 volts to 33 kV, and that is connected to the wind farm collection point. And then after that, we will have another transformer to connect to their main grid of the transmission system. So basically from the wind turbine, we convert kinetic energy in the wind to the mechanical energy, and then we convert that mechanical energy to the electrical energy. Permanent magnet synchronous generator-based wind turbines, they surpassed the market share of double-fed induction generator-based wind turbines in 2017. So I have been researching wind turbines since 2014. Since 2010. So I have seen before DFIGs are very popular, but after 2017, the market share of MSG is increased drastically above the DFIG-based wind turbines. Permanent magnet synchronous generator is mainstream solution because of so many reasons like efficient energy production, gearless construction, which is one of the main attractive points for the offshore wind turbines, and it doesn't need any excitation. So the permanent magnets, they provide the excitation, and the control of permanent magnet synchronous generator is much simpler than the squirrel cage induction generator or double-fed induction generator. And also the reliability of the PMSG is very high compared to the SEIG or DFIG generators. In recent years, offshore wind farms are gaining a lot of attention because we can have more power and because of strong and steady winds in the offshore. Usually the permanent magnet synchronous generator based turbines are connected to the grid by back-to-back connected voltage source converter. So these voltage source converters are available in two categories like low voltage and medium voltage. I will talk about those converters in the next few slides. If we see the market share of wind turbines, we have top 10 wind turbine manufacturers in 2020. Number one position is from Vestas. Next one is Siemens. Third one is Goldwind. Fourth one is GE Energy. Next we got Envision, Mingyang, Windy, Nordex, and Shanghai Electric and CSIC. So if we see also we got the total gigawatts of power installed by these companies. And then if we see the technologies used by these companies, we have 9 out of 10 top 10 wind turbine manufacturers using PMSG. So we can see here, Vestas is using PMSG, Siemens, Gamesa, Goldwind, GE Energy, Envision, Mingyang, Windy, and Shanghai Electric and CSIC. All these companies, they produce large turbines based on PMSG technology. They also have DFIG and SCIG technologies that are used for the medium power, like 3 to 5 megawatt power ratings. And growth in the size of the wind turbines, starting in 1980s, the turbine size was 50 kilowatts. And over the years, the size of the turbines, they increased drastically. So we can see it surpassed the height of Statue of Liberty in around 1998. And then by 2015, we got turbine size so enormous, which is 10 megawatts. The size of each blade is equal to Boeing 747. And by 2020, we got already 15 megawatt wind turbines in the market. In the current market, wind turbines above 5 megawatt, they dominate the market. We will have 15 to 20 megawatt turbines by 2020. So we have 15 now. We can expect even higher power ratings in future. There are so many companies working on these large turbines like Clipper, Sway Turbines, Sinovel, Mitsubishi, Goldwind, Mekal, Mingyang, United Power, GE Energy, and Gamesa. If we see the largest turbines, Siemens and Gamesa, they have a 14 megawatt version. GE have 12 megawatt version, and Vestas, they have 10 megawatt version. So here we can see pictures of large wind turbines. This one is from Vestas for 9.5 or 10 megawatts. This is Siemens Gamesa for 8 megawatts. This is Goldwind for 6.7 megawatts. GE Halliday, that's for the 6 megawatts. They have the updated version for 12 megawatt as well. Mingyang is for 6 megawatts. Adwen is for 5 megawatts. So here in this slide, I got the most powerful turbine in the market, which is GE Halliday X, which is for 12 megawatts. In recent days, they Gamesha, Siemens Gamesha, they announced 14 megawatt wind turbine, but we don't have technical details. So I just put 12 megawatt one here. Its power rating is for 12 megawatts and rotor diameter is 220 meters. The blades are 107 meters long. It is 260 meters high, and it has capacity factor of 63% and swept area of 38,000 square meters. It's a very powerful turbine. If you compare the height of this turbine with respect to Eiffel Tower, which is 1,063 feet, this turbine is 853 feet. And then if we compare to the Chrysler building, this is 1,046 feet, very tall and very powerful turbine. Next, I'm going to switch gears and I will talk about power converters for PMS-GVX. So the power converters for the wind turbines, they can be broadly classified into 4 categories. One is back-to-back connected converters, where we have one type of converter for AC to DC conversion, and then again, DC back to AC. So because these 2 converters are identical, we call these back-to-back connected converters. Next one is passive generator side power converters. So here we do AC to DC conversion by diode rectifiers. And then we have DC to DC boost converter. And then we convert the DC back to AC by inverter. So here we got power converters for multi-phase generators where we can have 6-phase or multi-phase generators. We use multiple windings and then we cascade the outputs and then convert AC to DC. We can do this one back-to-back configuration, or we can do with passive generator side. That's why I put the DC-DC stage in the dash line. So we can also implement that one in with passive generator side. Next, DC to AC conversion is common. Then we got the last category, which is power converters without intermediate DC link, also called matrix converters. They convert variable voltage, variable frequency to fixed voltage, fixed frequency. Among all these categories, back-to-back connected converters, they have highest market share. In the past, we have passive generator side converters in the market, but the newest turbines, they are not using diode front ends anymore because of the high torque ripples. And we have some commercial products for the multi-phase converters. And also we have medium voltage matrix converters available in market, but they are not operational yet. So the first one is back-to-back connected 2-level voltage source converter. So we got the wind turbine. With the PMSG, as we talk, we can eliminate the gearbox and then we can design the generator with large diameter. So the PMSG is the main focus here. The output of the generator is connected to the rectifier, 2-level voltage source rectifier, also called machine side converter. Converts AC to DC. And then here we got regulated DC link. And then the DC is converted back to AC by the 2-level voltage source inverter. If we see the construction of 2-level VSR and 2-level VSA, they are identical. The switching devices are implemented by the low voltage insulated gate bipolar transistor. The output is connected to the step-up transformer through harmonic filter like L filter or LCL filter. And then the output of the step-up transformer is connected to the wind farm collection point. This converter can be used up to 750 kilowatts. That is the capacity available in the market. There are some companies that produce now converters up to 800 kilowatts or 850 kilowatts now. And they can operate up to 1000 volts line-to-line voltage. These converters offer bidirectional power flow and complete decoupling between the generator and grid. So if there is some fault on the grid side, the generator do not see that fault because it is isolated by the back-to-back connected converter. This is very popular one employed by over 50 wind turbine manufacturers. So if the power rating of the turbine increases over 750 kilowatts, we can increase the power rating by connecting the converters in parallel. So whatever the converter we see before, that is one converter here. By connecting more converters in parallel, we increase the power rating. So We have this configuration used up to 10 megawatts, and then still low voltage, that is 1000 volts. The features of these parallel converters is that they are modular, so we can connect as many converters as we need. It is redundant, so if one converter fails, system can still work with the remaining converters. We don't need to shut down the turbine, and they are more reliable. This is employed by, this configuration is employed by over 40 wind turbine manufacturers. The next configuration is multi-phase. So if I go back to previous slide, so if we see here, these converters are connected in parallel. So when we have these converters connected in parallel, we have a problem of circulating currents on both generator side as well as grid side. We can avoid the problem of circulating currents by using a multi-phase generator and then multi-phase transformer. So here, because the windings are electrically insulated, we don't have the problem of circulating currents, and then we still have all the benefits that we discussed earlier. This topology is available up to 4.5 megawatts and 1000 volts. This is commercialized by Gamesha with up to 4.5 megawatts with 6 modules in parallel. The next one is back-to-back connected neutral point clamped converter. So the two-level converters are replaced by now three-level converters. So here we got the NPC rectifier, we got NPC inverter. The DC link now consists of two split DC link capacitors. So this is the midpoint. So this converter operates at medium voltages. So medium voltage is 3000 to 4000 volts line to line. And it is now available up to 6 megawatts. We can even increase the power rating beyond 6 megawatts. This can be used with CIG, PMSG, or one rotor synchronous generator, but it is mainly popularized by the PMS.
Sorry, Venkata, by mistake, I turned off your microphone. Can you turn off again? Sorry.
Okay, so this converter enables medium voltage operation. So because of the medium voltage, now here the currents are decreased on the grid side. And when the currents are decreased, the I square R losses in the cable are decreased. And also the size of the cable becomes smaller. And the cost analysis indicates that this turbine operates with the low cost of energy. And the power quality is better because we have, three-level waveform on the output side. So the harmonic filter requirement is lower. And also for the given harmonic filter size, we can have better power quality. And also the cable size becomes lower. These converters are commercialized by ABB, Ingi Team, Convert Team, Areva, Shandong, XCMC, Darwin, and Jpress. So this is very popular configuration in the market for medium voltage operations. Next, I talk about passive generator side converters. So this is the configuration commercialized by Vensis and Goldwing up to 1.5 megawatts. So here we have diode rectifier to convert AC to DC. So here we use 6-phase diode rectifiers with 30 degrees phase shift between the 3 phases. So with this phase shift, we can cancel 5th and 7th harmonics. When we cancel 5th and 7th harmonics, that's where we have major harmonics, and then we can eliminate the 6th harmonic in the torque, and then we will have smooth torque. And here we got 3 boost converters operating in parallel. So they are interleaved converters. Each converter handles 500 kilowatt. And then on the grid side, we got 2 inverters operating in parallel. So each converter is for 750 kilowatts. So this is from the old Vensis and Goldwyn products. If I look into the website of Vensis and Goldwyn, they are not making any new products based on this technology. Every commercial product is now available based on back-to-back technology, but this is quite interesting to know that we have had some commercial products based on diode rectifiers. The features of this topology is that it has low generator current ripple and it is modular, so we can increase more boost converters in parallel. We can connect more inverters in parallel to increase the power rating. So similar to the low voltage passive generator side converters, we can also achieve medium voltage with the passive generated side converters. So we can connect diode rectifiers in series, and that enables medium voltage operation for the AC to DC stage. And then we can have a 3-level boost converter. So that is used for medium voltage operation. The output of the 3-level boost converter directly fits the cascaded capacitors. And then the output is inverter is based on neutral point clamped inverter. And the output of the inverter is connected to the grid through harmonic filter and step-up transformer. This is the topology that I was proposed during my PhD. It is not commercial, but it is very promising. It combines the low-cost diode rectifier with efficient NPC inverter. This topology can be used up to 6 megawatts and 4,000 volts. Now I will talk about control of permanent magnet synchronous generator based VEX. So here we can see onshore or offshore PMSG VEX with HVDC transmission. So we got the generator, gearbox, generator, which is connected to AC to DC converter, also called machine state converter. So we got DC chopper here. That DC chopper is enabled during the fault right through. So if there is some fault, we need to inject only reactive power to the grid, and we need to limit the active power coming from the turbines in order to limit the active power. So whatever the active power already produced, that's going to be dissipated in the resistors. So that is done through the DC choppers. And then we have grid state converter, DC to AC conversion, and then harmonic filter and step-up transformer. So this is called wind farm collection point. That's where several other turbines are connected. And then we have this wind farm collection point connected to the onshore grid through offshore converter, which is AC to DC. But this is operating at very high voltages because we got the offshore transformer increasing the voltage to 130 kV or 230 kV. And then we transmit the power with the DC cables. Usually these are submarine cables. And then once we have the cables reaching onshore, we convert the DC back to AC. And then we connect the output of the AC to the onshore grid. And then when we talk about control, we have the control of the machine state converter, control of grid state converter, and then again, we got control of offshore and onshore converters. For all these converters, we need to take care of fault right through. If I go more details into the PMSG-VX and I talk about the control requirements, on the generator side, I need to control the generator speed, torque, or power in order to achieve maximum power point tracking. That is the primary control objective. And also secondary control objectives are like, I need to reduce the switching frequency because we are talking about megawatt level application. In order to decrease the losses, we need to decrease the switching frequency. And if I have back-to-back connected neutral point clamped converters, I also need to control the neutral point voltage. On the grid side, we have more control requirements, like we need to make sure that we maintain this DC link voltage at constant value. And also we need to synchronize the inverter to the grid. And also we need to control the reactive power on the grid side. And also we need to perform fault right through operation. Secondary control objectives are similar to the generator side. So we need to reduce switching frequency and also control the neutral point voltage. So no matter what is the type of the topology, we need to achieve these primary and secondary control objectives. Then I talk about three control techniques. One is classical control. Next one is predictive control. Then the other one is the recent topic that myself and also Professor Marco Rivera are working rigorously, that is modulated predictive control. So the linear control is just linear model for the proportional integral controller and converter model for the space vector modulation. So here the controller design is based on PI adjustment and modulated design. This controller is linear, so it is not going to produce the best performance because the system is non-linear. Mostly in the industry, it is implemented by digital, though it can be implemented analog. So it needs modulation. The switching frequency is fixed. Here we got the, in multivariable control, we got the coupled control. So that means that if we are doing current control in DQ axis, so the D axis current impacts Q axis current control. So we need to have some decoupling loops in order to mitigate that. We cannot include the constraints in the control. So we need to change the modulation stage or other parts of the control in order to include the constraints. So that's not so easy. Complexity is medium. Steady state performance is excellent in DQ frame, and transient performance is moderate. Computational burden is medium. So so if we see the major advantages and disadvantages of the linear control, we got fixed switching frequency, which leads to low steady state errors. But because of the modulator, the transient performance is not so good. On the other hand, we got the predictive control. The switching frequency becomes variable, but the transient performance is really good, but the steady state performance is not so good because of the variable switching frequency. Now, combining linear control with predictive control, we have the new version, which is modulated predictive control. It produces fixed switching frequency and low steady state errors, same like the linear control. And also it produces excellent transient performance like the predictive control. Now the modulated predictive control uses cost function and also modulator similar to the modulation stage of the linear control. I will talk about these three controls with respect to the permanent magnet synchronous generator based wind energy systems. Predictive control is just like playing chess. So we predict what is the opponent move. We can predict so many steps ahead. If I move this like this, he is going to move like that, then I can move like this, and then I can move like that. So we can predict based on your imagination power, you can predict 5 or 6 steps ahead. So that is prediction. And then you are going to optimize your moves based on the number of the strength of your power. And then receding horizon strategy. So we just repeat the same thing over and over again. So MPC is recently commercialized by ABB. In 2016, they made model predictive torque control for Mega Drive LCI systems. In 2018, they made model predictive pulse pattern control for ACS 6080 system. So they are for the megawatt level applications. It's quite interesting to know that ABB commercialized, and it's not so surprised because ABB already have direct torque control and direct power control schemes, which are based on variable switching frequency, and MPC operates with variable switching frequency. They have the technology and methods to mitigate the problems with the variable switching frequency. So we got new products based on classical predictive control operating with variable switching frequency. But most of the products in the market are based on fixed switching frequency. So some of the few slides that I talk here that achieve the best advantages of classical linear control and the predictive control, they are very promising for the drives and wind energy systems. So here we got the linear control, I think 30 minutes. So maybe next 5 to less than 10 minutes, I will finish. So classical control, which is linear control based on 0 D-axis current control or maximum torque per ampere control. So here we got anemometer. We measure the wind speed. Based on the wind speed, we get speed reference from the maximum 4-point tracking algorithm. And then we compare to the speed, and we use a PA controller which gives torque. Based on the torque and feedback IDS current, we can calculate DQ axis reference currents and then compare them to the feedback DQ axis currents. We use PA controllers and some compensation terms. We get DQ axis reference voltages, convert them to ABC frame, and then do the pulse width modulation, and then control the switching states of the devices here. So that is the classical control. So here we're using PWM. So we have a fixed switching frequency and low steady state errors. But the drawback is that we have a sluggish dynamic performance. This is a standard strategy used in several wind turbines. Next one is a classical direct torque control. So we got the speed reference, same like before. And then we have the torque reference. Based on the torque reference, we get the stator flux reference. And then we use torque and flux relays. And then the outputs of the torque and flux relays is given to the lookup table. And then the lookup table directly produces the switching signals. So if we see here, we don't have modulator, so the output is going to be variable switching frequency. So we are going to have better response for torque and stator flux. But because of the variable switching frequency, the steady state errors are large. So these are the control schemes for the generator side. Now, if we look into the grid side, zero-day axis current control is quite similar to the voltage-oriented control. So they are the linear control. So we need to control DC link voltage and grid reactive power. So based on DC link voltage loop, we get the axis current. Based on reactive power loop, we get Q axis current. And then we use the PA controller, same like before. And then we get D and Q axis reference voltages converted to ABC frame. And then we use PWM stage to produce the switching signals. So the performance of UOC is similar to the ZDC control. We have fixed switching frequency, low steady state errors, but transient performance is sluggish. Similar to the direct torque control, we can use direct power control on the grid side. So here we use VDC reference, from which we calculate reactive power reference. Reactive power reference is given by the grid operator. Here we use relays, produces the error in the active power and reactive power by lookup table. We produce the switching signals to the inverter. So again, this performance similar to direct torque control, variable switching frequency with fast transient response, but very large steady state errors. So next we got predictive control. So predictive control is quite different. It has no modulators or no PA controllers. So we get speed reference similar to the classical control. From the speed reference, getting D-axis reference currents and Q-axis reference currents. So this part is similar to the classical control. Once we have D and Q axis reference currents, we extrapolate them to the K+1 state, because the cost function computes the error in the future state. So we need to convert it to K+1 state. So we see the design procedure. First one is that we measure the stator currents, DC link voltage, wind speed, and generator speed and position. Next, we estimate the rotor angle, which is theta R, and here. And then we calculate the reference stator currents, that is the stage here, similar to the linear control. And then we extrapolate the reference currents to the K+1 state. And then we predict the future behavior of stator currents based on the available number of switching states in the converter. So for the two-level inverter, we got 8 possible switching states. So we get 8 predictions for the currents. And then we do the cost function minimization, and then we see which switching state has the lowest error. And then we take that switching state and we apply to the inverter. Now, if you see, the PA controllers act upon the error. So they act once the error is already happened. But the predictive control, it predicts what is the error going to be in the future state. Based on the prediction, it's going to choose the switching state that's going to reduce the error. So it's like, the linear control is like a remedy method that is going to reduce the error once it's already happened. Whereas its predictive control is like cautious method that it's going to reduce the error before it does happen. So that's the main difference between linear control and predictive control. Next, we talk about predictive current control for the grid state converter. So design procedure, we measure grid voltages and grid currents, and we estimate the grid voltage angle through the phase lock loop. Then we convert ABC grid voltages and currents to DQ frame. And then we calculate reference currents similar to the classical VOC control. We extrapolate them to K+1 state. And then we predict the future behavior based on the possible switching states. And when we do the cost function minimization, and then we choose the switching state combination that produces lowest error, and then apply that switching state combination to the inverter. So we don't have any modulator here. So both the PCC for generator and grid state converter, they operate with variable switching frequency, but the transient response is very fast because there is no modulator stage. The variable switching stage frequency produces large steady state error. So we got two different classes that produce different characteristics, but in the industry, we want some technique that is promising to replace the linear control. So it needs to be, it needs to offer the same advantages like fixed switching frequency and low steady state errors, but it needs to make more improvements like improving the transient performance. That's what the topics that I have been researching nowadays. So here I got modulated predictive control. So the overall control is same like before. So until here, this part is classical control. So the cost function directly applies the switching states. But in the modulated control, instead of choosing the switching states, we choose the voltage vectors and their corresponding dwell times. So we got the space vector diagram. So previously we choose according to the minimum switching, the switching state combinations, so 8 combinations, but now we choose which sector. So we got 3 vectors, one vector here, one vector here. So V, V, V. So we take the trigonometric properties and then we choose 3 vectors in one sector and we take what is the average error for that sector. Then we move to the another sector and then we take what is the average error for that sector. So we calculate the average error for each of the 6 sectors. And then we choose the sector that produces the lowest cost function value. So when we choose that sector, we have 3 corresponding voltage vectors. So if we see here, so we got 1 voltage vector in the middle and 1 voltage vector here, 1 voltage vectors here. So if I choose this sector, so I got 3 adjacent voltage vectors. So I take those voltage vectors and also I can calculate the dwell times for those voltage vectors. Once I have the voltage vectors and their dwell times, I can perform the 7 segment switching scheme similar to the classical space vector modulation, and then I can apply the switching states based on the switching sequence. So therefore from here I can see that I got the classical predictive control and I got switching state sequence from the classical space vector modulation. By combining these two, I can have the benefits of the both control schemes. I can have fixed switching frequency, low steady state errors, as well as I can have fast transient response. This block diagram is from a recent paper that we published in 2020. This paper is available on IEEE Explore, so you can refer to that paper if you need more information. Next one is modulated predictive control for back-to-back connected NPC converters. So it's the same thing like before, but now we got 3 adjacent vectors for the 3-level inverter, and then the switching sequence is going to change for the machine side converter and grid side converter. Based on the switching sequence, we can control the dislink capacitor voltages, that is the neutral point voltage. And also we use 7 segment switching sequence in order to produce the switching frequency, constant switching frequency. So this paper is also recently published in 2020 in ECCE conference. I think this paper just came today or yesterday. Future trends, I think this is my last slide. We have more bigger turbines like 15 to 20 megawatt turbines already announced by several manufacturers. We can see more larger turbines. The reason is large turbines produce more power, and the initial cost of the turbine is going to be lower. So a large turbine is more efficient and economical compared to the group of the small turbines. So we can see more large turbines, but these large turbines are going to be deployed offshore. And gearless wind turbines in the offshore, the maintenance cost is very high if we need to do any maintenance on the gears. So the gearless turbines, also called direct drive turbines, are going to be very promising for the offshore deployment. Because of the huge power ratings, the size of the PMSG is going to be very high because of the direct drive operation. The size is already very high and the volume is very high. So if we go for 20 megawatt rating, it's going to be enormous. And then in order to decrease the weight and volume of the generators, we can use high temperature superconducting generators. This is already offered by AMSC, that is American Superconductors. So that company produced a 10 megawatt PMSG wind turbine for wind turbines. We have HTS generators available in medium voltage drives up to 33 megawatts. So the technology is already there. We can use it for wind turbines as well. Right now for the medium voltage operation, so as we are going towards multi-megawatt, above 15 megawatt, low voltage operation is not trendy anymore. We need to use medium voltage operation for such high power ratings to reduce the losses and increase the power quality. Right now in the market, we have only NPC converters, but we can anticipate more efficient converters like active neutral point clamped converter, or modular multi-level converters, etc. Right now, the market uses silicon-based devices, but in future, we can expect wide band gap devices such as silicon carbide. And right now, we have HVDC transmission, classical one, but with a lot of new wind farms being installed, we can expect multi-terminal HVDC transmission systems for the wind farms. Fault rate through control right now is implemented by DC choppers, dissipating the surplus energy in the DC resistors. But that is not an efficient method. Rather, it's going to be more advantageous to store that surplus energy. So having energy storage systems with each turbine or at wind farm level is going to be more advantageous and more better to curtail the output of the wind turbines to make it smoother. And also we have with a lot of wind power integration into the existing grids. We have a lot of recent grid codes changing rapidly, and these wind turbines need to meet these grid codes. So that emphasizes the control part. We can see more advanced control schemes at wind turbine and wind farm levels in order to increase the energy conversion efficiency and also to meet the grid codes. So one of the promising techniques is predictive control. That's all. Thank you very much. If you have any questions, you can ask me now, or if you get any question after this presentation, feel free to send me an email at this email address. Thank you all for your attention, and I'm open for discussions now.
Thank you very much, Venkata, for your interesting presentation. Very, very interesting. Now, I would like to ask Professor Fredrik Ladger to provide some comments and some questions for you, if there is any.
Sure.
Okay. Yes, thank you. Very interesting presentation and fantastic overview about the technology. I have a few questions to the things. As one thing is that the permanent magnet generators seem to take over the double-fed induction generator market.
Right.
10, 15 years ago, there was a high, let's say, demand, or not high demand, there was not enough production of permanent magnets. How do you see this prediction in the future? I know some companies, they were jumping out using permanent magnet generators because the permanent magnets became too expensive. Do we have any indication about if that is a risk in the future, that the permanent magnets will not be available?
Last part, because I just lost the connection.
Okay, my question is, are there enough permanent magnets available to support the future generator industry?
Oh, that's a quite interesting question. Right now, most of the PMSG, permanent magnet materials, are processed in China. And, we have this trade war going with US and China. Because of that, it's quite, interesting how it's going to be in future. Right now, China is the main supplier of the permanent magnet materials. If that's also a political thing that we need to consider. So if it is going to be more tougher trade between China and other countries, it's going to be required. So PMSG might be replaced by the squirrel cage induction generator.
Okay. Okay. If this trade war will go on.
Yeah.
Okay, some of your solutions are moving into medium voltage generators.
Right.
Do you see any challenges in applying medium voltage generators in the turbines? Is it the same design or protection schemes in the generators? Because as I could see, we are moving up, let's say, to 2 or 3 kV generators.
Right.
Yeah.
So the generator technology is not changing that much rapidly compared to the converters or the semiconductor devices. So the wind energy industry is just adapting the technology from the electric drives. Whatever is the proven technology in the electric drives, the technology.
So the medium voltage drives from,
So in the electric drives, we have PMSGs available up to 33 kV medium voltage, but when it comes to the wind turbines, we are only using up to 3 kV. But it is quite possible that in future we can have, for example, there are two companies that produce not the permanent magnet generators, but wound rotor synchronous generators, WRSG. So they are type 5 turbines where they don't use the electrical converter, rather they use the mechanical converter. So those turbines are commercialized by Vico company and some other company. So those two companies produced 3 megawatt wind turbines at 13.8 kV.
Okay.
So in future we can see higher medium voltages. So that's going to open the room for researching more novel medium voltage converters. Probably MMC is going to be more suitable candidate if we go for 13.8 kV.
Yeah. Having such high voltage in the turbine, is that a challenge?
Insulation wise is not a challenge because the wind turbines, they have this natural cooling process. So they design the kind of ducts to cool the generator. They put it at the starting of the blades so that they use the natural flow of the air to cool the generators. In terms of the cooling, it's not a problem to go for higher medium voltages. The wind energy industry is very reluctant for the technology change. So we can see in future some higher medium voltage operations, but they don't take risk with millions of dollars on the wind turbine, because turbine, the cost of the turbine is less than 50%, but the planning and commissioning of the turbine is more than 50%, right? So they don't want to take the risk like in the medium voltage drives, where you just buy the motor and converter and put it in the operation. So whatever the technology they take, they want to make sure that it's well established in the drives industry before they adopt it.
That's maybe also wise to do, because the risk can be high if you fail on the market, and the margin is not so high. So it's good to be careful. Okay, maybe my last question in this round, as there are also other panel members. So you discuss a lot control using model predictive control, and this is being applied a lot. We also know that there are constraints in terms of power quality and design of the output filter for the grid connection. Do you see any challenges in that respect to, let's say, to do the filter design when applying a non-fixed switching frequency? I don't know if you have any experience with that.
When I worked with classical predictive control, so switching frequency is variable. So normally we take for the two-level converters like anywhere from 15 to 20% of the grid impedance. And for the medium voltage converters, we go like 10%. So we use that one and then run the simulations and experiments, see what is the THD. Based on the THD, we just try to optimize based on the closest value of the inductor available. I don't do any specific research on optimizing the filter design based on the variable switching frequency. But now my focus is shifted towards fixed switching frequency predictive control. Now with the fixed switching frequency, the grid filter design is quite similar to the linear control.
Absolutely. Absolutely. Then you know what you have.
Yeah.
Okay, thank you this time, Marco. I think there are also others who should raise some questions.
Yeah, thank you very much, Frede. Jose Luis?
Yes, thank you very much, Dr. Yaramasu, for your excellent presentation about permanent magnet synchronous generator-based energy conversion systems, which have been gaining market share in recent years. As you have said, have surpassed the FIG in 2017. I am convinced that wind energy, along with solar PV, will be the most important renewable energies facilitating the world energy transition.
Yes.
And the wind power share of global electricity demand is expected to be between 18% to 41% by 2015 and 50, excuse me, depending on the policy scenarios to be implemented. And this data is according to the Global Wind Energy Council. For example, if the growth ratio from 2015 to 2019 remains the same, then by 2050, the wind power share of global electricity demand could be 25%. That would be a lot of share of electricity generated just by wind power. So also from data freely available online, in 2017, the permanent magnet synchronous generator direct drive, the gearless option, wind turbine technology, had a 21.6% of global market share, according to FTI Intelligence, a market analysis company. And in 2018, it had a 20.8% according to the International Renewable Energy Agency. So with this combination of permanent magnet and direct drive, the market share is about 22%. And the conventional drive, the options of DFIG, squirrel cage, permanent magnet, with gears, equipped with gears, is still the preferred technology with nearly 70% of market share. And well, I am also an enthusiast of model predictive control, as you know. And I find very interesting the different approaches to address the drawbacks when presented in the classical form of predictive control. Like the examples you already said, variable switching frequency corrected with modulated model predictive control, the weighting factors calculations of the cost functions tackled with artificial intelligence techniques, the delay error when it is compensated when prediction horizons are expanded, and so on. Every drawback that is presented to model predictive control has been tackled, but I haven't seen a wind energy conversion system announced to have a power converter based in model predictive control yet. So with this being said, I'm going to ask a few questions. How do you foresee the adoption of the industry for model predictive control applied in wind energy conversion systems? Is it already happening? Is it going to happen soon? What are your thoughts about it?
Okay. So that's a lot of information and quite a few questions. I think let me come, if I remember correctly, it's morning time, so I think my memory is working very good. I can mostly answer most of the thoughts that you gave. So wind turbines installed capacity is keep increasing. That means we have more wind turbines along the highways. So we have more spots to get out of the car and take the Instagram photos. So that's one good thing. The wind turbines, you said anywhere from 5% to 41% in the present scenario. Yes, that depends on the country and how much electricity they are generating. Right now, we have Denmark, which already surpassed 50% wind penetration. It depends on the countries, and in US we got 6% penetration. There are some countries, China produces a lot of electricity from wind, but in terms of their generation and consumption, so the penetration rate is lower. But definitely we can see increase in the wind penetration in the coming years. Despite the government policies, still several countries doing great. So you know that in US, Trump is not pro renewable energy, but still we got so many states pro renewable energy, like California state, Texas. They are installing more and more wind turbines. So if we see specifically in US, we got some mid states where we have supplied more than 50% of the electricity usage from the wind. So some states are doing really, really good with the wind energy. So that's answering one of your thoughts. So other thought is that you say that the direct drive is 22.6%, 22 roughly percentage. You said that remaining 70% market is from the SCIG and DFIG. When I talk about the top 10 wind turbine manufacturers, so you can see the gigawatts of installed capacity. So I don't know where you got those numbers, but I assume that you might not have considered PMSG with 3-stage gearbox. So there are some commercial products in the market, not only direct drive, but the PMSG is available with the 3-stage gearbox. Probably they have more share than the SCIG and DFIG. So yes, there is DFIG technology in the market there. That is the second largest technology that uses 3-stage gearbox. But SCIG is doesn't have too much market share right now. So it's used in the fixed speed turbines. They don't have too much technology. So that's regarding the gearboxes. So what is the other thing?
Yes, when I was talking about the conventional drive and its market share, I wasn't talking about the generator type, just the technologies that had a gearbox has the preference of the clients in 70%. That's what this firm of market analysis says.
If you see if we use direct drive technology, the diameter of the PMSG becomes 5x larger, and the weight is also going to be 5x larger. Heavy, it's very large diameter and heavy. So that needs special design. So it needs to have more stronger foundation. So special construction requirements and all those things. That's why mostly the direct drive technology is going to be used for the offshore wind turbines. The technology is shifting. So as I mentioned, the future trends, one of the trend is going to be direct drive technology.
Nice. So finally, what would be your personal prediction for the wind power share of global electricity demand by 2050?
That changes a lot by the politics. So if this seminar is delayed by 24 hours, I can tell you more clear answer. If Biden wins, we are going to have more renewable energy support. If Trump wins, it's going to be support there, but still less. So it depends on the government, depends on the foreign policies, etc. But it might be a bit slower or might be a bit faster, but we are going to see the trend of going up all the time. It's not going to go, the cumulative capacity or the annual capacity is not going to go down. It's going to still go up every year, but it depends how fast we are going to climb up based on the government policies, incentives, and the foreign policies, etc. So I think the last one is about MPC adoption for the wind energy. So as I mentioned, wind turbine manufacturers are highly reluctant to the new technologies. They will not employ anything new until it is proven in the industry, in the electric drives industry. So right now, MPC is adopted for the drives, in the medium voltage drives by ABB. And if we have some future companies adopting MPC or modulated MPC for the drives, if they are performing very well and it has good performance over the years, then the wind engine industry will adopt it. Basically, the same companies produce the technology for the wind. For example, ABB, they have medium voltage drives, and ABB produces the turbines, the converters and the control schemes for the wind turbines as well. So it's the same company. They first test it in the medium voltage drives. Then if it is successful, then they will move it to the turbines.
Thank you. Thank you very much, Dr. Yaramasu. That'll be all.
Thank you very much, Jose. Now, Ruben.
Yeah, okay. Well, yes, thank you very much for a very, very interesting presentation. I had a few questions, but I think two of the panelists have already asked about that. But I think I've got one or two left. One is regarding the power converter. Do you see any future or any tendency in using direct AC power converters in wind power applications?
Yes. So as I have talked in my slides, Escava, they have this Anavine, that's the name of the product. They made, I think, 9x9 module multi-modular matrix converter, MMMC. So they made that converter for wind turbines targeting medium voltage operation.
All
So
right.
they made the converter, but to my knowledge, there are no companies that have used the Escavas converters.
All right. What power is that? Excuse me. What power is that wind turbine?
So they made up to, I think, 6 megawatts of the capacity.
6 megawatt. Okay. And well, as you mentioned in your presentation, permanent magnet synchronous generator or one rotor synchronous generator are overtaking double fed induction machines
Right.
in wind power application. But is there any manufacturer still using double fed induction generators in the market or not?
Yes. So all those companies that I talked. So if you see the
Yeah,
slide.
yeah. I saw 5 of them. Yes.
So if we go to the so Vestas, they still produce turbines based on DFIG, and GE Energy still produces, Envision still produces, Mingyang still produces based on DFIG technology. So
Yeah.
uh,
Yes.
major companies still using DFIG. So it's not dead. DFIG is not dead. Still, it
Yeah.
is in
Okay.
the
Yeah.
market.
It is because of the. My question is because of the grid code requirements
Right.
are more difficult to accomplish by double fed induction generators than
Yeah. Another
magnet synchronous machines.
for shifting from DFIG to the PMSG is the offshore deployment, where
Yeah.
the DFIG needs regular maintenance for these slip rings and brushes. So usually every 3 months they need to do the maintenance. So the
Yeah.
maintenance
Okay.
cost of the offshore turbines is quite high compared to the onshore turbines. Because of that, the technology is shifting towards the PMSG.
All right. Well, yeah, thank you very much for your presentation and for your answers.
Thank you. It's honor meeting you.
Me too, yes.
Thank you, Professor Peña. Thank you to our speaker and all the panelists. We have I will say to you all the questions. We have a lot of questions, and we have a very broad audience, international audience actually. That reflects the importance of this technology, wind energy, wind technology. So I would like to ask to begin. Well, I think Professor Peña already said something about the question of what is the trend regarding the use of these direct drive generators. Okay, and this is another question from Carlos Reuser. What are the current development of using synchronous reluctance generators for wind energy conversion systems? Maybe Professor Venkata, can you respond that, please?
Yeah, sure. Switcher reluctance generators are used, in some electric vehicles for a few hundred kilowatts in the drives, but there are no megawatt wind turbines based on switcher reluctance generators. There might be some small companies producing 5 kilowatt, 10 kilowatt generators based on switcher reluctance. My focus is not on the small turbines, rather I research large turbines. To my knowledge, there are no commercial turbines based on switcher reluctance generators, megawatt level turbines.
Thank you, Professor Venkata. What are the current control challenges? Can MPC make the difference compared to the classical control? I would like to hear from Professor Blackger, if you can say something about that. Can MPC really make a difference applied to these systems?
Oh yes, there was a very good reference in the presentation that ABB has applied MPC on drive control, right? So I think this is an indication about that MPC can be applied, and maybe already is applied because, to my knowledge, ABB technology is also already in some of the wind turbines. So maybe without we know it exactly, it is already applied one way or the other. I don't know, but it could be, because I know some ABB drives which are applied in some of the big turbines. We had a short discussion about the grid side and MPC, and I think the question there will be as how the optimization is done filter-wise, because the filters are quite expensive. When we are in those big scales, everything counts in terms of weight and so on. So if MPC perform better, then it's attractive. If it's too risky to apply MPC in terms of certain designs, because MPC is a little bit non-linear, dependent on the working conditions, then the other one could be the winner. So yes, I think it is already applied, but in some of the control issues, I think we are a little bit. It's not so big difference finally, because we can make shaft torque, we can produce power into the grid system. So it's let's say marginal things which are being improved, but still worth to go for.
Thank you, Professor Blanchard.
Some comments to that question.
Yeah.
If you want to make any control technique commercial, if it needs to be successful, there are two things that we need to consider. The first one is that it needs to perform better than the existing control. And secondly, it needs to be easy and simple to understand for the people, right? So if you remember, there are so many tons of works before on fuzzy logic control, artificial neural networks for the electric drives. Most of the works were published by Professor Bimal K. Bose, but if you see, there are no commercial products based on fuzzy logic network or artificial neural networks, because the topic is quite complicated. And if you are talking about commercialization, it's not only the people who design it, but all the technicians work in the company, they need to understand, because they need to go to the site to do the repair and all those things. The technique needs to be simple. The linear control is so popular because it is quite easy to understand. So the 2 points, one is enhanced performance, second one is simplicity. So if we have these two qualities, then MPC can be found in commercial applications.
Thank you for your comments on that, Professor Venkata. Regarding to that, there's another question that is related to that from Camilo Gonzalez. The MPC for the control of the PMSG is only developed in academia. I know he says that I know that the FOC control or PI control in DQ reference frame is more usual in the industry. Jose Luis, maybe you can add something about that.
So yes, so
yeah.
PI control. I mean, when they develop, ABB develops, modulated predictive torque control. So they need to consider both induction motors and permanent magnet synchronous motors. So that modulated predictive torque control is going to be, that converter can feed induction motors and permanent magnet synchronous motors. So the control is going to be calculation of the DQ axis reference currents is going to be different for different motors. So that MPDC model predictive torque control from ABB, I think it's going to be applicable for both the motors, induction motors and permanent magnet synchronous motors. But I see that there is a huge trend among the Chinese academia for the predictive control. So I was in Pre-Seed conference last year in China. I see that almost from every university, they are working on the predictive control. One thing that I like from the Chinese academia is that they have very good connections with the industry, and the turnout time to convert the theoretical knowledge to the product for them is very short. So whether it is going to be good or bad, they're going to give it a try. So they can make this predictive control for the drives for the low power rating commercial product. And then if it is successful, it is successful. If it is not, they're going to improve it. So I can see that in future, if we are going to see more success from predictive control, that might come from China.
Jose Luis, would you like to add something on that?
Yes, I would like to add that, like has been already said, before 2016, everything was published in the academia. After 2016 and in 2018, like Venkata already said, we have a ABB naming a model of a converter applying model predictive control. So this is a big event for us who are enthusiasts of model predictive control, because we have already known before 2016 that they were doing a lot of research on model predictive control inside ABB, and now presenting this product to the public, it gives a lot of impression that it will be applied by the industry in the near future. So yes, before it was already only academia work, but now we have evidence that it's going to be also the industry work.
Thank you, Jose Luis. Professor.
Just a minute.
Yes?
We add this to one. I have this ABB presentation where let me show you the two commercial products. It's going to be quite interesting for the audience. So this is the ACS 6080 drive. And they use the pulse model predictive pulse pattern control. And if you see the advantages with this technology is that it has 50% reduction of the current distortion, 50% reduction of the switching frequency, up to 50% increase of the output speed, and 10% increase in the output power. So these are the real catching numbers for those markets. So you don't need to, I mean, when you're talking to the industry guys, those who are not experts with these things, if you're talking to some consumer, these are the numbers that are going to be more attractive. So you don't need to talk to them about cost function, weighting factors, and all those things. These are the numbers that they care most, like what is the improvement in the drive system. So if we see
that's quite interesting.
They have more power from the same power hardware. They have smaller drive footprint. They have longer life, higher energy efficiency, reduced downtime and maintenance, and higher system efficiency. These are the advantages that they promote from the MPC drives. ABB, these are the catchy points they use in the market to attract the consumers. So I think that is my 2 cents for MPC drives commercialization.
In that sense, there appears another question. This question actually now is from Maria Inés Valla, regarding the modulated MPC. Maybe Professor Peña can say something about that. How high is the computational burden of this control strategy applied to this? What can you say about that, Professor Peña? Activate your microphone, please.
Okay. Yes. Yes. Well, nobody listens to me most of the time, so it's okay to have the microphone off. Well, I don't see any problem with that. With the modern technology in with microprocessors, I don't see the computational burden will be a problem for applying these techniques. I mean, most of the time, the people that work in the academia with applying using this technique, they don't even care in optimizing the code, right? So because the microprocessors or the DSP are so fast that nobody wastes time in trying to get an optimal code. So I don't see any problem the computational burden is not a problem for applying these technologies. This is my view. Okay.
Okay, thank you, Professor Peña. In that same line, more or less, there's another question from Camilo Gonzalez. Again, sorry, but it's related to this topic. What are the software for microcontrollers used in the real industry applications? I mean, he's saying that DSP plus FPGA or PLC. He says that he knows that for the servos in the pitch angle control, they use the PLC. Maybe Professor Bludger or Professor Venkata? Professor Bludger.
Oh, I think it's a combination. They have extremely fast processors to do the fast loops. No doubt about that. So, and that means they can do a lot of things. And then, because a wind turbine is not just a current controller, there are a lot of functions, many mechanical parts, monitoring, communication, and so on. So PLCs and so on are also used to control the overall system. So it's multiple. It's really multiple controller structure, but of course done in a smart way in order to also have a redundant communication system and redundant control system and so on. So I think they have the whole, let's say, the whole range of possibilities, which in the last end, they have tried to optimize also in terms of cost.
Thank you, Professor Bludger. Professor Venkata, would you like to add something on that?
I agree. The processors available in the market, they are quite fast enough to handle these calculations. Beyond these calculations, I can say.
Okay, there was. Let's move to another side of this technology. There was a question from Professor Bludger to you, Professor Venkata, about the availability of the magnetic materials. Okay, regarding taking into account that, in your opinion, which are the limits? Maybe if there is another one, in your opinion, which are the limits for the development of higher power wind power PMSG? What?
The last sentence.
In your opinion, which are the limits for the development of higher power of this sort of permanent magnet synchronous generator? I mean, is there any other besides the availability of these rare materials for permanent magnet?
Okay. I think I gave my thoughts. I think it's going to be very useful for the audience to listen from Professor Bludger. He's quite expert on the PMSGs as well. I think I will add my comments after Professor Bludger.
Okay, Professor Bludger.
Oh, but honestly, I'm not really on the top of all this market on different material and so on. But at that time when there was this closed down, or let's say trade war between the continents, which maybe still are there, I think it was really a wake-up call for the wind turbine industry that this could be a high-risk part of the wind turbine. So they had to look at other places to have the source. So, but it's relatively. I'm relatively sure that the supply is more reliable now, because otherwise we will not see this progress. And I also know some mines have been opened around the world, because when the price go up, then mines are also opening up, because then it makes sense to open them up. But as the wind turbine generator market is going up, the demand will also go up, right? So it's always a balance between supply and what is needed in the market.
Thank you, Professor Bladger. Regarding to this permanent magnet as well, from Osvaldo Michelau, sorry about my pronunciation of. Is there any data about the demagnetization of the permanent magnet after 10 or 15 years of use? Jose Luis, can you say something about that?
So the current materials used for the PMSG, they market as a very low rate of demagnetization, but how well they perform is not quite enough time to comment on that. Maybe we need to wait a couple of more years to see some companies commenting that, oh, that demagnetization is too much or something. But I think they have these technologies in place to nullify that demagnetization effect.
Yes, I might add as a advertisement that in our next session we will have this Master in Sciences Alejandro Yoki, who is working with Vestas, who is involved in researching and investigating about that precisely, the magnetization of permanent magnetic synchronous generation of when there is severe faults in the generator. So it happens with severe faults, and yes, it will happen eventually in time, because the energy stored in the magnet is going to be released somehow. So he will be the guy who will respond that the next session.
Okay, thank you, Jose Luis. Regarding to that, I mean, we have a lot of questions, from the audience, because the topic is very interesting. I would like to add to the panelists, to our speaker, if you are available 15 more minutes, or we can be closing. Are you okay, Professor?
Because there is opening of a conference in Aachen here at 3 p.m. here, EGWIT.
Okay.
Maybe I jump to that one and be a part of the opening. But if there are any other questions, you're welcome to mail to me. So it's just I want to be on that opening, because it's a Power Electronics Society conference. So I think it's most fair I show my face there.
No problem, Professor.
It has been a pleasure.
Yeah, well, there's a lot of questions. We would like to your last comment. Professor Bladger, you had to leave. We would like to hear your last comment on this.
Oh, it's an excellent session, very interesting. I believe wind and solar, they are the two main player for the next decades we are looking into. So it's just to move on to make the technology better, safer, and more cheap, because it is already cheap, but it can be even more cheap. And it's an amazing technology. 20 megawatt of wind turbines. This is a fantastic construction. So thank you for inviting me, and I wish you a continuous good seminar, and I'll try to join the next one coming up also. So thank you.
Thank you,
Thank you, Professor. Thank you very much.
Bye-bye. Thank you.
Bye-bye. So, sorry.
Bye. Thank you. Your last comment, Professor Peña, we would like to hear.
Oh, yeah, well, some time ago, I was in a meeting with other people in Santiago, Chile, and people were a bit worried because of the pandemic and the impact that could have on the use of renewable energy in the country and also in the world, because the economy activities is going down in most of the countries because of the pandemic. So the question was, is there any better future for renewable energy, considering that the demand of energy will go down? And it was an interesting question, but we can see that even when the pandemic is in its height, the project in wind power applications and in solar application are still doing quite well. And you can see recent news that wind power plant being project and other being installed in Chile. So I think probably renewable energy is even more powerful than the virus. So this seminar is very, very good because it can share more knowledge on wind power applications, the new tendencies, and what the future could be for this technology. So it's very interesting, and I appreciate the talk that Professor Venkata, and a very interesting one. And I think people will carry on working and doing research in wind power application, and that is very good.
Thank you, Professor Peña. Jose Luis, your last comments on this, please.
Yes, I totally agree with the comments of Professor Dr. Rubén Peña, and I would like to take this opportunity to thank a lot Dr. Venkata Yaramasu for his time, for his presentation, and the panelists also for their opinions, their comments. Thank you very much for inviting me to this event. And I also appreciate very much the opportunity to speak about wind energy technology, to try to make a lot of people think about the benefits of renewable energy and how we all can contribute to make a better world with the usage of technologies which do not pollute our environment. So thank you again, and looking forward for our next meeting. Thank you.
Okay,
We will
so
be there. Professor Venkata.
Before we hang up, I think I'm reading the comments of the audience. I may quickly answer some of the comments. Someone, I think I answered this for Professor Peña about direct AC converters. Someone is asking, has the modulated predictive control been applied to NPC back-to-back converters? Maria, yes, it's been applied by me and my team. The paper just came yesterday online to IEEE. Someone asking about prediction Arjan. Yes, we use one-step prediction Arjan and maybe two-step for the dead time compensation. And Professor Kojo is asking about slides of the presentation. I send the slides, but I have the updated slides. I will send it to Christina and Marco, and probably they can circulate the slides to everyone in this meeting.
We will share the slides. Yeah, it will be available. Marco?
Yeah, I would like to say thank you very much to my colleague and my friend Venkata Yaramasu. We have been working together since 2009, 10, I think, so long time ago. And it's my real pleasure to see what are you doing in your work at your university. So thank you very much for sharing with us this interesting presentation. Thank you as well to Fred, to Ruben and Jose Luis for their support. And now I would like to give the screen to Cristina, because she will invite us for the next and final session. Cristina.
Thank you, Marco. Thank you to all. Thank you to the audience for this interesting session and very, very participative. I'm sorry that we couldn't, due to the time, we couldn't make all the questions, we couldn't pose all the questions, but I'm sure the panelists, as they say, they are willing to answer them through the email, and you can check. There are many questions that have asked about this slide. You can check it on our YouTube channel. So, and there's the link that Marco has posted in the chat. We would like to invite you to our next and final session of this 2020 webinar, because this is the last one for this year. And Mr. Elizondo, who has accompanied us today, is going to present. So I'm going to share the banner so you can check. Yeah, there it is. There you go. So this would be in 2 weeks' time, on the 17th November, and the session would be Desarrollo y Tecnología de la Energía Eólica en el Mundo. So quite in the line of what we have talked today. So if you are interested, we will wait for you. We hope you join us. I will send you the links so you can join through Zoom or YouTube as today. So thank you all, and see you in 2 weeks. Bye.
Okay, thank you very much. See you next time. Okay, bye-bye.
Bye-bye. Thank you very much. Bye-bye.
Thank you.
Thank you very much, Venkata.
Yeah, you're welcome.
Thank you very much.